Welcome to ChemVid. Today we are going to be talking about nuclear chemistry, which is so cool and does amazing things. Let's get started. Alright, first off, radioactivity. A lot of these words you've heard before, but they have different meanings than how the public uses them, okay? So as we're going through this, make sure we know the chemical definition, not what the public says is the definition, alright? Alright. So, radioactivity. Radioactivity is the spontaneous disintegration of some elements into smaller pieces. Go ahead and write that down. What this means is elements will break apart into smaller versions of themselves. You guys have heard of this in the opposite direction. We learned that when you create elements, it goes through a process called fission, where two small elements become one big element. Well, this one is where you take one element and you break it down into two smaller elements. That's what radioactivity is. It's the process of that breaking down of elements. And Marie Curie was an amazing woman, and she was the one that actually discovered radioactivity. Alright, a nuclear reaction is a reaction that deals with the nucleus and is spontaneous. Fix that while I'm here. So, whenever we talk about a chemical reaction versus a nuclear reaction, a chemical reaction involves the electrons on the outside of the atom. A nuclear reaction involves the nucleus, protons, neutrons, inside. And that is the entire definition of a nuclear reaction. So, why do atoms undergo nuclear changes? Why would they want to break apart? Why would they want to come together? All those good things. Well, the answer is stability. If my atom can become stable by losing a little bit of mass or losing a neutron or a proton or something like that, that's what's going to happen. So when you talk about like uranium, plutonium, those are the types of elements we're used to breaking down, and they have pretty short half-lives. A half-life is just the amount of time it takes for a substance to break apart. Okay, so it just means that they break apart quickly. The reason why they do that is because once they break off a piece of themselves, what's left over is more stable. And that's why nuclear changes and nuclear reactions actually happen. And when you're looking at radioactive decay, nuclear decay, or that breaking apart, is spontaneous. You don't have to do anything to an element in order to get it to decay. It'll happen by itself naturally. Every single element does it. But some of them do it faster than others. Alright, so uranium, plutonium, they do it rather quickly, and that's why we use them for like nuclear energy and stuff like that. Whereas, like potassium or magnesium or helium or, those smaller atoms, they don't decompose that fast. In fact, their half-lives are like billions of years. It takes billions of years for them to break apart. So, everything breaks apart. Some do it faster. Another thing to know about radioactive decay is that it is exponential. Exponential means that it's not breaking apart, it's not a linear pattern, but instead it breaks apart and the graph will curve upwards. You guys have seen this in math class. X squared, x cubed, those types of things. They have a curved slope instead of a straight line. So when we're talking about decay, we're talking about decay that happens in an exponential way. If I have a total amount of a substance, it decays by half. Then it decays by half again. Then it decays by half again. Then it decays by half again. And when I graph that data, I get a nice exponential line. Alright, so nuclear versus chemical. We basically already covered this, but just in case. Nuclear involves the nucleus. Chemical involves the electrons. Now, the most important thing that you want to remember from this, we're going to go over chemical reactions later, but the reason why nuclear power has so much power is because of the binding energy, okay? So, in a nucleus, you have protons and neutrons, and they are put together, and that's what forms the nucleus. Well, the energy that holds that nucleus together is called binding energy. And so when you're trying to break apart a nucleus or get a proton or a neutron out, you have to overcome that binding energy, and that takes a lot of outside energy. So the reason why a nuclear blast is going to give off so much more energy than, let's say, a chemical reaction like a bomb, okay, TNT, that can produce one heck of a punch. But nuclear explosion, that's kind of like the stuff you learned about in World War II in Japan, where it leveled the place and left devastation where it went in like that entire area. So nuclear reactions are much stronger than chemical reactions. And the reason why is we're dealing with the nucleus and that binding energy that's inside. Alright, so let's jump down and talk about changes in the nucleus. Fusion and fission. Fusion you've already heard about. Fusion is where we take two little nuclei or two little atoms, put them together, and it creates a new atom. Fission is the exact opposite. I take one big atom and I split it into two little atoms. Okay? So fusion is coming together, fission is splitting apart. And I have a little cup for you. Oh boy, I'm hungry. Me too. What's in the fridge? Just a couple atoms. Want to split them? Sure. Some people find that a little morbid, but I find it funny. So I hope you guys enjoy. Alright, let's move on. We got fusion, fission, lots of breaking apart. Lots of coming together, and it's all about the nucleus. Alright, so we need to be able to write these out. In middle school, you guys learned how to write chemical equations. Nuclear equations are very similar to that, except for the only thing we care about are the protons and the neutrons. So if I look at this equation right here, I need to know that this is the mass number. The one on the top is the mass number, the protons and the neutrons. The number here is the protons. And in a reaction, I cannot lose any protons or neutrons. We talked about the law of conservation of mass. And the law of conservation of mass includes protons, neutrons, electrons, all that good stuff. So on both sides of the equation, I need to have 92 protons. On both sides of the equation, I need to have a mass of 238. So if I look over here, uranium is going to break apart into thorium and a helium atom. Helium is number 2 on the periodic table, and it has a mass of 4, which means that thorium is created because I need to have 2 plus 90 equals 92, and 4 plus 234 is 238. So basically it is addition and subtraction. Can you find out which is which? Over here we're talking about alpha, beta, and gamma radiation. This guy right here, that helium atom, is known as an alpha particle. Alpha particles do alpha radiation. So in this case, this would be alpha radiation. So let's try example number 2. I know it says we'll do it in class, but we're gonna do it now. Alright, for example number 2, I am told that rubidium-81, or rubidium with a mass of 81, is going to undergo some type of fission, fusion, right here, to create a new thing. So what I'm going to do is I am going to do some basic math. 37 minus 1 is 36. 81 plus 0 is 81. But how do I determine what this particle is? Like, what is this? If you told me that it was because of the protons, you are right. Or I do it with the protons, you are correct. Protons tell me the identity of my substance. So what I'm going to do is I'm going to take a look at the periodic table. and I am looking for number 36. 36 protons. So I'm going to look, and I find that 36 is krypton, and so I write krypton right there, and my equation is complete. When rubidium reacts with, this is called a beta particle, it is going to create krypton with 36 protons and 81 protons and neutrons. So coming back to your notes, this equation right here, the rubidium one that we just did, should be right here under example number 2. This particle right here is called a beta particle, so this is an example of beta radiation. There are 3 types of radiation that are the main types, all right? The first one is called alpha radiation, and it's a nucleus of a helium atom. So you can write it one of 2 ways. Helium 4-2, or you can do a little alpha symbol like this with a 4-2. Either work, both are correct. And it has a +2 charge because it's the nucleus and there are no electrons around it. Beta is an electron. It has a -1 charge, and you can either use an electron symbol or you can use a beta symbol. Now you may be saying, hold on, Miss Powell, I thought you said that nuclear radiation was all about protons and neutrons. And you would be correct. I did say that. Protons and neutrons are the main thing. But electrons are sometimes involved in nuclear radiation. But protons and neutrons are the majority, and that's what we focus on. Protons and neutrons are always messed up when you're doing this type of radiation. All right, moving down to gamma. Gamma is what we call pure energy. It's not a particle, and it doesn't have a charge. But when you have gamma radiation coming off of something, you have like a lot of energy, all right? And we use this little squiggly Y symbol to represent gamma. So looking at these guys, you can see that alpha rays can be stopped by a piece of paper. If you're wondering where you need to write this, scroll down a little on your notes. Aha! Fill in the boxes. So, an alpha particle has a charge of +2. Its symbol is a little squiggly line. Somebody calls it a fish sometimes. And as a shield, you can use a piece of paper. A piece of paper will stop alpha particles. And they can only travel about 2 to 4 centimeters. Beta particles, on the other hand, they have more energy. They could go straight through a piece of paper, but they will be stopped by 0.5 centimeters of lead. Okay, so a beta particle has a -1 charge. It's got a little B, fancy B for its symbol, and you can shield yourself with 0.5 centimeters of lead. Also, thick clothing will actually stop this as well. So if you're putting on, like if you have a big thick coat on, that will stop beta particles as well, because they can only travel about 2 to 3 meters before they die out. Gamma, on the other hand, is the strongest one. It doesn't have a charge. Its symbol is the cute little Y thing. But in order to shield yourself from gamma radiation, you need 10 centimeters of lead or 10 feet of concrete. You have to have a lot of protection to stop gamma radiation. It can travel 500 meters, which is 4.5 football fields long. So you would have to be able to run away from this gamma radiation. You would have to instantly go from one end of a football field to the other end 4 times and then get to the half-yard line. Gamma radiation is extremely strong and it can travel really, really fast. All right, so for homework, I would like you to fill in this chart with the correct symbols and the correct numbers that go with them to match these particles. Neutrons and protons can be found right here. This is their symbol, so go ahead and fill those in. And then I'd like you to try writing these nuclear equations. But I do want to start with this first one and give you some hints. So write the nuclear equation for the alpha decay of polonium-212. Well, alpha decay means that I am going to have an alpha particle, which looks like this. Polonium-212 means I have a polonium atom with a mass of 212, so the 212 goes up there in the mass number. Decay means that the helium or the alpha particle is coming off. So I'm going to draw an arrow. It's going to release an alpha particle and create something else. That's what you have to figure out. Good luck!